In this video, we are going to conclude the topics for chapter 3, part 1. We are going to talk about section 3.3, which is titled Ionic Compounds, Electron Give and Take. First, we are going to learn how to utilize the information of cations and anions to write the chemical formula for an ionic compound. And then we're going to proceed to practice, if we're given a chemical formula, how do we name that particular formula for an ionic compound? So here we have an example for the steps that need to follow when you need to write the chemical formula for an ionic compound. I'm going to read the steps, then I'm going to proceed to do the 3 examples that we have on the slide. First step, you need to write the symbol for the metal cation and its charge. Next, you're going to write the symbol for the non-metal anion and its charge. Step number 3, you're going to take the value of that charge without the sign, and you're going to make that the subscript of the other ion present in your molecule. Then, if necessary, you're going to reduce the subscripts to a whole number that has the smallest ratio. Let's look at the following examples. So the first ionic compound is going to be composed of magnesium and bromine. So if I have magnesium, from my knowledge of the periodic table, since magnesium lives in group 2A, that means that magnesium is going to have a charge of +2. You may write +2 or 2 positive. It is okay to write either way. So when it comes to magnesium, I write the symbol for magnesium. That's step 1. I write the charge of magnesium. Since it lives in 2A, it's going to have a +2 charge. Then I look at the next element, which is bromine. The symbol for bromine is going to be Br. Since bromine lives in group 7A, then its charge is going to be -1. In step 3, it says that I'm going to take the charge without the sign and make it the subscript of the other atom. So that means that overall, I'm going to take this value of 2 and I'm going to make it the subscript of bromine. I'm going to take a value of 1 and I'm going to make it the subscript of magnesium. So as a result, when I write my chemical formula, I'm going to write Mg1Br2. One of the things that I'm going to add to the rules here is that a subscript of value 1 is omitted. So when I look at my chemical formula, I see that magnesium has a value of 1, and since I need to omit it, then I'm going to erase that value of 1. So the final answer for the chemical formula when magnesium and bromine come together to make an ionic compound is going to be MgBr2. Let's move on to the next example, which is where we have an ionic compound that is formed by calcium and oxygen. Let me start writing the group numbers for each. Calcium lives in 2A. Oxygen lives in 6A in the periodic table. So going back to my rules, for my metal cation, which is always the first element that I see in ionic compounds, I write the symbol for calcium, which is Ca. Since it lives in 2A, I'm going to place a +2, 2+, whichever way you want to write it. If you write +2, that's okay also. Then I write the symbol for oxygen. Because oxygen lives in 6A, then this is going to be a -2. Then I'm going to do step 3. In step 3, as you can see, this value becomes the subscript of the calcium. This value becomes the subscript of the oxygen. So when I write my chemical formula, I'm going to write Ca2O2. As you can see, in this case, we are going to be applying that fourth rule that I mentioned that says that you're going to reduce the subscripts to the smallest whole number ratio. And the reason why I can do this is because the value of 2 can be divisible. So if overall I divide both sides by 2, that means that this becomes Ca1O1. And as I just illustrated, a subscript of value 1 is omitted. So the final answer for this chemical formula is CaO. In the last example that we have specifically elements that are placed in other tables that I provided in the slides. Now, we can see that this ionic compound, in the third example, we see the element iron, and we see in parentheses a Roman numeral. Next to it, we see carbonate. Understand that carbonate, you're not going to find it in the periodic table. Carbonate, you, from memorizing the polyatomic ions, should be able to identify that it is a polyatomic ion. So iron, since it is a transition metal and it has variable charge, the Roman numeral is the charge of iron. So the symbol for iron is Fe. The charge, because we see a Roman numeral 3, is +3. Remember that metals, including transition metals, always form cations. Carbonate, from the list of polyatomic ions, you can identify that it is CO3 and its charge is specifically -2. We've moved to step 3, in which we are going to take this value of 3 and make it the subscript of carbonate. This value of 2, we make it the subscript of the iron. So at first, when we write the chemical formula, we write Fe2CO3, and there's a 3 outside. But if you look at that chemical formula, it kind of looks weird because it looks like CO33, and that is not possible. The interesting thing is that when we have polyatomic ions and they have a subscript larger than 1, we need to put parentheses around it. And this is only for polyatomic ions. So to correctly illustrate that there's going to be a subscript of 3 assigned to the carbonate after we exchange the values for specifically the charges, we need to put it in parentheses. So let me just write a note here. Polyatomic ions that result in having subscripts of value larger than 1 need a parentheses and the subscript is outside. So please don't confuse this with the subscript that already pertains to the polyatomic ion. CO3 is the unit. So that's why you put it overall in the parentheses. The 3 is the incoming subscript that it receives. That's why it's placed outside of the parentheses. To solidify this, let's actually go through a few examples. Here, let's proceed to do specifically problems B, C, and D. So the ionic compound on letter B is going to be formed from strontium and iodine. The ionic compound on letter C is made out of manganese and oxygen. And the ionic compound in letter D is going to be made from sodium and nitrogen. So let's do problem B. In problem B, let's write the group number for each of these. So strontium lives in 2A, iodine lives in 7A, manganese is a an element that lives specifically in the transition elements. That's why you see the Roman numeral. We don't need to write the group number. Oxygen lives in 6A. Sodium lives in 1A. Nitrogen lives in 5A. So let's do problem B. As you can see, we have strontium. Strontium has the symbol capital S, small case r, and its charge is going to be positive 2 because of its group number. Iodine is a nonmetal. Its symbol is capital I because it lives in 7A. It has a charge of -1. Then I'm going to take the charge without the sign and I'm going to make it the subscript. So this means that I'm going to write SR1, I2, and because the value of 1 is omitted, the final answer for a compound, an ionic compound made out of strontium and iodine is SRI2. Let's move on to problem C. First, I have manganese. The symbol for manganese is going to be capital M, small case n. Since I see a Roman numeral 4, then let's understand that that means that positive 4 is its charge. Remember, things that are metal are going to be cations. Then I have oxygen, which is a non-metal. Oxygen has a symbol of capital O. Because it lives in 6A, it has a charge of -2. So when I take the charge without the sign and I make the subscript, I find that overall I have Mn2O4 as my chemical formula. Now, the value of 2 and the value of 4 are divisible by one another. So I have that extra step, step number 4. This a specific chemical formula needs it. So I'm going to divide both sides by 2. So my final answer is Mn1O2. And since the value of 1 is omitted, then I can erase the value of 1. Lastly, on problem D, I have sodium and nitrogen making a compound. So first I write sodium, which its symbol is capital N, small case a. Since it lives in 1A, it has a charge of +1. Nitrogen, its symbol is capital N. Since it lives in group 5A, it has a charge of -3. So when I exchange the charge, I find that my chemical formula is Na3N1. And since 1 is omitted, then my final answer is Na3N. Make sure that you practice the other problems that you see on the slide. The last thing that we are going to go over is if we have a particular chemical formula, can we specifically write the name of the ionic compound? As you can observe here, we have 5 steps overall. There is some information on the right side of the slide. So I'm going to be using my laser pointer, going over each of the steps, and then we're going to apply it in the problems that we have in the next slide. So these are the steps for naming ionic compound. When you're giving a chemical formula and you need to name it, so remember here, we are given a chemical formula and we need to find its name. We first have to identify the cation and we have to identify the anion in the chemical formula. This is why it is essential that you know which ones are your metals, which ones are your nonmetals, which ones are the polyatomic ions. As you can see in step 2, your cations are going to live in group 1A, group 2A, group 3A, or you're going to have cations that are zinc, cadmium, silver, or you're going to have cations that are variable charge, like the elements in group B, except these 3 that I only have 1 charge: tin, antimony, lead, bismuth. Those are your cations. So if you have a cation that you can see in rule 2 that have only 1 charge, then understand that you're going to do only the name of the element to write the name. If you have cations that are variable charge, you need to quote unquote break the chemical formula, and then you're going to assign the charges to the ions, and then you're going to use the name of the element for your variable charge, and then in parentheses, you're going to use a Roman numeral for representing that variable charge. For your anions in a chemical formula, understand that they're going to come from 2 sources. They're either going to be a single nonmetal, and those single nonmetals are living in 5A, 6A, or 7A. You can see the ions that are formed, and in the last column, you can see the name of the anion. You need to memorize those names: nitride, phosphide, oxide, sulfide, so on and so forth. The other type of anion that we have are going to be if they're polyatomics. Remember that there's only 1 cation that is a polyatomic, which is right here in the corner, ammonium. The rest of them are going to be anions. And if your chemical formula has a polyatomic anion, you use the name of the polyatomic. Now, let's actually practice because it's the best way to learn for going from chemical formula to the name of a compound. So I'm going to do here a few examples, so at least you're able to visualize overall how is it that we do the following problems. For just doing some of these, we are going to do letter C, letter D, we are going to do letter F, and lastly, letter I. Make sure that you practice how to go from chemical formula to name with the problems that I did not highlight. Let's get started with letter C. In letter C, we have magnesium and we have nitrogen. Now, if we overall remember from the knowledge that we have of the periodic table, you should identify that magnesium is going to be one of those cations that only have one charge because it lives in group 2A. So as the rules mention, if you have a cation, which is always the first element that you have in a chemical formula, then you just write the name of the element. So for letter C, the first word in the name of this compound is going to be magnesium. The second word here will be the name that we give a nitrogen ion. And if you look at the table in the previous slide, that is nitride. Let me go back into the slide so you guys see which rules that I used. So for naming that magnesium nitride, I used rule number 2, because my cation, magnesium, lives in 2A. So I only utilize the name of the element. When it came with my anion is the second element in my chemical formula. Since the anion came from a nonmetal, and the name is going to be given in this table, nitrogen as an anion, the word is nitride. And that's how I obtained that information. Let's go to the next example. In letter D, we have NiCl3. So NiCl3, from looking at the periodic table, you should recognize that nickel lives in group B. That chlorine, in other words, Cl, in this case, is going to be one of those nonmetal ions. As it says in the rules, if your cation lives in group B, we need to break the chemical formula. And let me illustrate how that quote-unquote break occurs. The quote-unquote break that we are going to be performing is that you will take this value and you're going to assign it back to the nickel. Next to the nickel, we don't see that there's a number. And remember that the value of 1 is always omitted. So there's actually a value of 1 right here. And that is assigned back to the chlorine. So if I break this Ni1Cl3, that means that this came from Ni plus 3 Cl minus 1. Then I have to ask myself, is my anion the correct charge? Meaning, is chlorine always -1? If we look at the table that we have here, you can observe that the chloride ion is always -1 because it lives in group 7A. So that chemical formula and how I broke those ions, now I can name. So for the correct name, I'm going to write the name of the element, nickel, then this number 3, it is represented as a Roman numeral. And then I'm going to place the name for the ion of chlorine, which is chloride. So in order to name this ionic compound, I utilize rule number 3 along with rule number 4, because those are my components of my compound. Let's proceed to letter F. On letter F, we also have nickel. So from example D, you should recognize, oh, I need to break that into ions because nickel has variable charge. How do I know what is the charge of nickel? Similar to what we saw in the previous example, the charge of nickel is going to be determined by the subscript in the neighboring ion. Now, you should recognize that when you have a polyatomic ion, and if that polyatomic ion has parentheses, then specifically the value outside of the parentheses is the charge that you need to reassign to your cation. So what that means is that we are going to take this value of 2 and we're going to give it to nickel. Since nickel doesn't have a number, remember there's a 1, and then we are going to redistribute it to that NO3. So this chemical formula is formed from Ni plus 2, NO3, because that's a unit, that's a polyatomic ion, and it's -1. Remember that your anion, you always have to check that it has the correct charge. So when we look at where my polyatomic ions are, I can see that NO3 has a negative charge, meaning -1, and that's nitrate. So to write the chemical formula for letter F, this is going to be specifically nickel, Roman numeral 2. The name of NO3 is going to be nitrate. Lastly, I have, oh, before I move on. So the rules that I utilize to name letter F are a combination of rule number 3 and specifically rule number 5. Let's proceed to the last example. I have PbC2O4. This is why it's important that you know what is a polyatomic ion. So your first element is always your metal. If the first element is not a metal, then we're talking about a different compound, and we're not going to deal with those until part 2 of chapter 3. So right now we're only dealing with ionic compounds. So in here, overall, I see PbC2O4. You should identify that specifically this is going to be your metal cation, and that this whole thing is going to be your anion. And since you will be memorizing the polyatomics, you will see that this is a polyatomic anion. So as we proceed, we need to take into consideration, what do I do with Pb? Is Pb a single charge or multiple charges? When I look at my rules, I can observe that Pb is actually going to be one of those cations that if I find it in a chemical formula, I need to break the chemical formula. So when I break this chemical formula into its components, Pb and C2O4, I see that overall, there's not a lot of digits in the bottom. Because it is important that you know the polyatomic ions chemical formula, please do not assume that that 4 is going to go to Pb. That is incorrect. C2O4 is a unit. So the 4 or the 2 for that matter next to carbon is not going to go to the PB. In this chemical formula, the way that it is written is that there is a subscript of 1 on both. So that means that I have PB plus 1, C2O4 minus 2. According to the chemical formula, right now it looks like C2O4 is actually minus 1. Now, if I look at my polyatomic table, I can observe that C2O4 is negative 2. That's why you saw me write negative 2 at first. So, since this is the correct charge for oxalate, and that is what is not expressed here in my chemical formula, I need to erase it and write the correct charge for it, which is negative 2. So if I find that things have a subscript of 1, is because the charge on my variable charge is going to, when added to the charge of my polyatomic ion, is going to equal 0. So by doing that exercise, I can determine that my PB is actually plus 2, not plus 1. So what happens overall is that if I have a lead that is plus 2 and an oxalate that is minus 2, PB, when it receives a subscript of 2, and when C2O4 receives a subscript of 2, what I did overall is that I divided that 2 because they're divisible. So that's where the PB1 C2O4 1 comes from. And since 1 is omitted, that's where I end up with just PbC2O4. So for naming that last compound, the correct name for it is going to be lead, Roman numeral 2, oxalate. Make sure that you practice textbooks problems or other resources in class for going from chemical formula to name for ionic compounds.